Imagine standing at the edge of the most extreme object in the universe, not on solid ground, because there is no ground, not in ordinary space, because space itself has become something else entirely. You're approaching a black hole, and in moments, you'll cross a boundary from which nothing, not even light, can return. What happens next defies every instinct you have about reality. Time breaks down. Space twists into shapes that have no name. Your body stretches in ways that physics textbooks describe with cold precision, but that no human has ever experienced. This isn't science fiction. This is what the laws of physics predict would actually happen if you fell into a black hole. And the story is far stranger than any movie has ever shown. Before we take that final plunge, we need to understand what a black hole actually is. Not the Hollywood version with swirling vortexes and mysterious portals, but the real object that emerges from Einstein's equations and lurks at the centers of galaxies. A black hole is what happens when gravity wins absolutely, when matter becomes so compressed that the fabric of space-time itself tears open, when the universe creates a region where the normal rules simply stop applying. To understand what would happen to you, we first need to understand what you'd be falling into, the nature of the beast. A black hole isn't a hole at all. It's not empty space waiting to be filled. It's the opposite, the most extreme concentration of matter and energy possible. Picture the sun, that massive ball of plasma that contains 99.8% of all the mass in our solar system. Now, imagine crushing it down to a sphere just 6 kilometers across. The density would be so extreme that a teaspoon of that material would weigh as much as a mountain. But that's not enough to make a black hole. You'd need to crush it even further, past the point where atomic structure collapses, past the point where even neutrons can't resist the pressure. You'd need to compress all that mass into a region smaller than the nucleus of an atom. At that point, something breaks in the universe. The curvature of space-time becomes infinite. The laws of physics, as we understand them, reach their limit. What remains is a singularity, a point of zero volume and infinite density where our mathematical descriptions of reality simply fail. Surrounding this singularity is the event horizon, the boundary that marks the point of no return. This isn't a physical surface. There's no membrane, no wall, no change in the properties of space that you could detect locally. It's simply the mathematical edge where the escape velocity equals the speed of light. Cross this line, and every possible path through space-time leads inward. There is no trajectory, no amount of thrust, no clever maneuver that can bring you back. The future direction of every possible world line points toward the singularity. The size of a black hole depends entirely on its mass. A black hole with the mass of Earth would have an event horizon just 9 millimeters across, smaller than a marble. A black hole with the mass of the Sun would have an event horizon about 3 kilometers in radius. Sagittarius A star, the supermassive black hole at the center of our Milky Way galaxy, contains 4 million solar masses and has an event horizon about 12 million kilometers in radius, roughly the size of Mercury's orbit. The largest known black holes span billions of solar masses, with event horizons that could swallow our entire solar system. Size matters when you're falling in, and we'll see why. Black holes come in different types, each with unique properties that would affect your journey. The simplest is a Schwarzschild black hole, named after the physicist Karl Schwarzschild, who found the first exact solution to Einstein's field equations just months after general relativity was published. A Schwarzschild black hole is non-rotating and has no electric charge. It's the theoretical baseline, the simplest possible black hole. In reality, these probably don't exist. Any black hole that forms from real matter would have some angular momentum, some spin inherited from the collapsing star or the swirling matter that fed it. But as a mathematical model, it gives us the clearest picture of what happens at the event horizon. More realistic is a Kerr black hole, named after Roy Kerr, who in 1963 solved Einstein's equations for a rotating black hole. Rotation changes everything. A spinning black hole drags space-time around with it in a process called frame dragging. Near the event horizon, space itself is being pulled around the black hole faster than light could move in the opposite direction. This creates a region called the ergosphere, outside the event horizon, where nothing can remain stationary. You'd be forced to move in the direction of the black hole's rotation, like a leaf caught in a whirlpool. The event horizon of a Kerr black hole isn't perfectly spherical. It's squashed at the poles and bulges at the equator, distorted by the black hole's rotation. Inside, the structure becomes even more bizarre. The singularity isn't a point, but a ring, a one-dimensional loop with no thickness. Theoretical paths exist through this ring that lead to other regions of space-time, though whether these paths could ever be traversed by anything physical remains deeply controversial. Then there's the Reissner-Nordstrom black hole, charged with electric potential, and the Kerr-Newman black hole, which has both charge and spin. These are probably rare in nature. Any charged black hole would quickly attract oppositely charged particles and neutralize itself. But they're important solutions mathematically, because they reveal possibilities in the structure of space-time that uncharged, non-rotating holes don't show. They have inner horizons, additional boundaries inside the event horizon where different physics applies. They have regions where causality breaks down in strange ways. They're consistent windows into the deeper weirdness of general relativity. For our journey, let's focus on a supermassive black hole. Not because it's the most common stellar mass black holes vastly outnumber their supermassive cousins, but because it gives you the best chance of survival, at least for a little while. The reason is tidal forces, and they're about to become your worst enemy. Tides that tear gravity doesn't pull uniformly. It pulls harder on things that are closer to the source. On Earth, this difference is negligible. Your head and feet experience essentially the same gravitational pull. The difference is measured in parts per billion. But near a black hole, this differential becomes catastrophic. The force pulling on your feet, the part of you closer to the singularity, can be billions of times stronger than the force on your head. This difference creates what's called a tidal force, and it will try to stretch you into a long, thin strand of atoms. Physicists have a term for this. They call it spaghettification. The name is playful, almost comical, but the reality is anything but. As you fall toward a black hole, the tidal forces grow exponentially. At some point, they exceed the molecular bonds holding your body together. Your tissues begin to stretch. Your bones elongate. The distance between your head and feet increases, while the width of your body compresses. You become a human noodle, stretched longer and longer, thinner and thinner, until even individual atoms are torn apart. The location where this happens depends entirely on the black hole's mass. For a stellar mass black hole, say 10 times the mass of the Sun, you'd be spaghettified long before reaching the event horizon. At a distance of perhaps 1,000 kilometers from the horizon, tidal forces would already be tearing you apart. Your body would be converted into a thin stream of atoms, still falling inward, but no longer resembling anything human. You'd be dead, thoroughly and completely dead, before, if you ever crossed the point of no return. This is why stellar mass black holes are essentially instant death traps. The event horizon and the spaghettification point are too close together. But supermassive black holes are different. The tidal forces at the event horizon depend not on the black hole's mass, but on its density gradient. A more massive black hole has a larger event horizon, which means the gradient of the gravitational field is gentler. For a supermassive black hole like Sagittarius A star, the tidal forces at the event horizon are surprisingly mild. They're stronger than you'd experience on Earth, uncomfortable certainly, but not immediately lethal. You could cross the event horizon intact. You could remain alive and conscious inside a black hole, at least for a little while. This is the scenario we'll explore, because it's the only one where there's actually a story to tell. Let's set the stage precisely. You're approaching a supermassive black hole, let's say one with 10 million solar masses. It's rotating, as all real black holes do, but not at an extreme rate. The event horizon is roughly 30 million kilometers in radius, about 20 times the size of the Sun. From a distance, it doesn't look like much. Space around you looks normal. Stars shine in all directions. But as you get closer, you start to notice distortions. The stars directly behind the black hole seem to bend around it. Light from behind is being curved by the extreme gravity, following geodesics through curved space-time. You're seeing gravitational lensing in real time. The black hole itself appears as a perfect circle of absolute darkness, blacker than the darkest night you've ever seen. It's not just an absence of light, it's a void in space where light cannot exist. Around this darkness is a bright ring, the photon sphere, where light orbits the black hole in unstable circular paths. Some of this light escapes outward, some spirals inward. The result is a brilliant halo, surrounding the shadow of the event horizon. If the black hole is actively feeding, consuming gas and dust from its surroundings, you might see an accretion disk, a vast spinning disk of superheated matter glowing with temperatures of millions of degrees. This disk wouldn't be visible in ordinary light. It would shine primarily in X-rays and gamma rays, radiation that would kill you long before gravity did. For our purposes, let's assume you're approaching a quiet black hole, one that hasn't fed recently, one where the space around it is relatively empty. As you draw closer, you notice something strange happening to time. You've brought a clock, and you're comparing it to clocks held by observers far from the black hole. According to your clock, time is passing normally, 1 second per second, as it always does. But when you look at signals from the distant observers, you see their clocks ticking faster. Not by a little, by a lot. Minutes pass for them while only seconds pass for you. This is gravitational time dilation, a direct consequence of general relativity. The deeper you are in a gravitational well, the slower time passes relative to observers farther out. Near the event horizon of a supermassive black hole, this effect becomes extreme. Let's quantify this. The time dilation factor depends on your distance from the event horizon. Far from the black hole, time flows normally, but as you approach the horizon, time slows down from the perspective of outside observers. At a distance of 2 event horizon radii, your clock ticks at about 70% of the rate of distant clocks. At 1.5 radii, it's down to about 58%. At 1.1 radii, just 10% beyond the horizon, your clock ticks at only 30% of the normal rate. And right at the event horizon itself, from the perspective of outside observers, time stops completely. You appear to freeze, suspended forever at the moment you cross the boundary. Light from your body becomes infinitely redshifted, stretched to wavelengths so long they become undetectable. To the outside universe, you fade away, never quite reaching the horizon, dimming into nothingness over the course of billions of years. But that's not what you experience. From your perspective, time flows normally. You look at your watch, and it ticks forward 1 second at a time. You think, you breathe, you exist in your own proper time. The outside universe, however, begins to look strange. Light from distant stars becomes blue-shifted, compressed to shorter wavelengths, higher energies. If you could survive long enough and look back, you'd see the entire future history of the universe play out in fast forward. Stars would be born, age, and die in moments. Galaxies would collide and merge. The cosmic microwave background would heat up as its wavelengths compressed. This isn't just theoretical. This is what the mathematics of general relativity predicts must happen. But you won't see any of this, because you don't have that much time. Crossing the horizon, you're now at the event horizon. In some descriptions, this moment is portrayed as dramatic, a point where space tears open or where you're violently pulled in. But the reality is stranger and, in a way, more terrifying. Nothing special happens. Locally, at the exact moment you cross the horizon, you don't feel anything unusual. There's no membrane to pass through, no sensation of transition. Space looks the same. Your body feels the same. If you didn't have sophisticated instruments to measure your position, you might not even know you'd crossed. This is one of the most profound aspects of the event horizon. It's not a physical boundary. It's a mathematical surface, a point in space-time where the geometry changes in a subtle but absolute way. The event horizon is a one-way membrane in space-time itself. Outside, there are paths that lead both toward and away from the singularity. Inside, all paths lead in only one direction. Forward becomes a direction in space, not time. Inward becomes a direction in time, not space. These statements seem like word games, but they're precisely what the mathematics shows. Before crossing the horizon, you could, in principle, fire your rockets and escape. After crossing, firing your rockets just changes which path you take to the singularity, not whether you reach it. The singularity isn't a place you're traveling toward. It's a moment in your future, as inevitable as next Tuesday. Let's talk about what you can see. Looking outward, back toward the universe you came from, things appear increasingly distorted. The sky compresses into a shrinking circle of light behind you. This is the Einstein ring. Light from the entire outside universe focused into a smaller and smaller region by the extreme curvature of space-time. Stars that were spread across the sky now appear to bunch together. The light becomes intensely blue-shifted toward higher energies. If you could see it, which you can't because your eyes aren't sensitive to these wavelengths, the cosmic microwave background would be glowing like a furnace. Looking forward, toward the singularity, you see darkness, not empty darkness like empty space, but a darkness that seems to absorb everything. This is the deep interior of the black hole, regions of space-time that light from outside has never reached. You're seeing into the future of the black hole itself. Some theoretical models suggest you might see strange structures. If the black hole is rotating, you might see the inner event horizon, a second boundary inside the first, where causality becomes even more distorted. Beyond that, the ring singularity, if this is a Kerr black hole, might produce strange optical effects. Some solutions to Einstein's equations allow for paths that pass through the ring into other regions of space-time, other universes perhaps, or other parts of our own universe connected through a wormhole. But these solutions are almost certainly not physical. They require exotic matter with negative energy density, matter that probably doesn't exist. They require the singularity to be perfectly stable, which quantum effects would almost certainly disrupt. The truth is, we don't know what you'd see in the deep interior. General relativity stops giving reliable answers as you approach the singularity. The curvature of space-time becomes infinite. Quantum effects that are normally negligible become important. We need a theory of quantum gravity to describe what really happens, and we don't have one. String theory, loop quantum gravity, and other approaches offer hints, but nothing conclusive. The inside of a black hole is a region where physics breaks down, where our maps of reality have blank spaces marked, "Here be dragons." But let's continue with what we do know. You're inside the event horizon, falling toward the singularity. How much time do you have left? This depends on the mass of the black hole and your trajectory. For a non-rotating black hole, the time from horizon to singularity is finite and calculable. For our 10 million solar mass black hole, if you fell straight in from rest at the horizon, you'd have about 5 minutes. 5 minutes of proper time as measured by your watch, before you reach the singularity. This isn't very long. A stellar mass black hole would give you a fraction of a second. A billion solar mass black hole might give you several hours, but in all cases, the time is finite. There's no escaping the singularity. It's not a question of if, but when. As you fall, the tidal forces grow. Remember, at the event horizon of a supermassive black hole, these forces were mild enough that you survived. But they're increasing exponentially as you approach the singularity. At some point, they exceed the strength of molecular bonds. Your body begins to stretch. This isn't painful at first because your nerves are stretching too. The signals from your feet take longer to reach your brain because the distance is increasing. But soon, the forces exceed what biological tissue can withstand. Cells rupture, bones fracture. Your body disintegrates into a stream of molecules, then atoms, then subatomic particles. This is the spaghettification we talked about earlier. It was delayed by choosing a supermassive black hole, but it's not avoided. Eventually, it happens to everything that falls in. What happens at the singularity itself? This is where general relativity genuinely breaks down. The equations predict infinite curvature, infinite density, infinite tidal forces. These infinities are a sign that the theory has reached its limit. In reality, something else must happen. Some physicists believe that quantum gravity effects become important at a scale called the Planck length, about 10 to the minus 35 meters. At this scale, space-time itself might not be smooth, but discrete, made of individual units, like pixels on a screen. The singularity might be replaced by a quantum foam, a seething mass of virtual particles and fluctuating geometry. Other models suggest the singularity might be a point where space-time connects to another region, perhaps another universe entirely. One particularly bold idea is that the interior of every black hole contains a new universe. When matter collapses past the point where quantum effects dominate, instead of forming a singularity, it bounces back, creating an expanding region of space-time that looks, from the inside, like a Big Bang. From outside, it's a black hole. From inside, it's an entire cosmos. This model, called the fecund universe hypothesis, suggests that universes reproduce through black hole formation, and that our own universe might be the interior of a black hole in a larger parent universe. It's speculative, probably untestable, but it illustrates how little we truly understand about what happens at the singularity. The information paradox. Here's where things get truly strange, and where physics enters territory that's still hotly debated. When you fall into a black hole, what happens to the information about your quantum state? According to quantum mechanics, information cannot be destroyed. The state of a quantum system, no matter how it evolves, always retains enough information to reconstruct its past. But according to general relativity, anything that falls into a black hole is lost forever. It's destroyed at the singularity, or at least removed from the observable universe. These two principles seem to contradict each other. This is the black hole information paradox, and it's been troubling physicists since Stephen Hawking first pointed it out in the 1970 seconds. Hawking discovered that black holes aren't entirely black. They emit radiation, now called Hawking radiation, through a quantum mechanical process that occurs near the event horizon. Virtual particle pairs, which normally pop into and out of existence in empty space, can be separated by the horizon. One particle falls in, the other escapes. The result is that the black hole slowly loses mass. Over an incomprehensibly long timescale, trillions upon trillions of years, a black hole will evaporate completely, leaving only radiation. Here's the problem. Hawking radiation, in its original formulation, is thermal. It contains no information about what fell in. It's just random heat. If a black hole evaporates completely and leaves only thermal radiation, then all the information about everything that fell in, every book, every person, every quantum state, is gone. This violates quantum mechanics. For decades, this paradox seemed unresolvable. Then, starting in the 1990 seconds, new ideas emerged from string theory and holography. The most promising is the holographic principle, which suggests that all the information about the interior of a black hole is somehow encoded on its surface, on the event horizon itself. The three-dimensional interior is a projection, a hologram, of information stored on the two-dimensional boundary. If this is true, then information isn't destroyed. It's scrambled, encoded on the horizon, and gradually released in the Hawking radiation through a process that's incredibly complex but ultimately unitary, preserving quantum information. Recent work has proposed that the information might be released through correlations in the Hawking radiation, correlations that only become apparent when you consider large numbers of particles. The radiation isn't purely thermal. It has subtle quantum correlations that, if you could measure them precisely enough, would allow you to reconstruct everything that fell in. This resolution, if correct, means that you're not truly lost when you fall into a black hole. Information about your quantum state gets encoded on the horizon, scrambled into an incredibly complex pattern, and slowly radiated back out over trillions of years. You're gone, your atoms are destroyed, but in some deep quantum mechanical sense, you still exist in the correlations of the outgoing radiation. This has bizarre implications. It suggests that there might not be a smooth interior to a black hole at all. Instead, the interior might be a kind of quantum mirror, a region where what appears to be falling in is actually being reflected in highly scrambled form. Some versions of this idea, called the firewall hypothesis, suggest that the event horizon might not be smooth, but instead might be a surface of incredibly high energy density, a wall of fire that would incinerate anything that tried to cross. This contradicts the equivalence principle, the idea that freely falling observers shouldn't experience anything unusual at the horizon, so it's controversial. But it shows how deeply the information paradox has shaken our understanding of black holes. What does this mean for you as you fall in? Honestly, we don't know. If the firewall hypothesis is correct, you'd be vaporized at the horizon, never making it inside at all. If the more conservative approaches are right, you'd experience roughly what general relativity predicts: smooth passage through the horizon, followed by inevitable destruction at the singularity. But your information would somehow be preserved in the Hawking radiation billions of years later. Or perhaps quantum gravity effects create some entirely different structure, something we can't predict with current physics. The interior of a black hole remains one of the deepest mysteries in science. The view from inside. Let's return to your subjective experience. You've crossed the horizon. You have minutes left. What do you actually observe? One thing you definitely don't see is other objects that fell in before you, not if they crossed at an earlier time. This is counterintuitive. You might imagine the interior of a black hole as a waiting room where everything that ever fell in sits around, anticipating the singularity. But that's not how it works. Space-time inside the horizon is structured so that past and future don't work the way they do outside. Objects that cross the horizon before you are already closer to the singularity. They're in your causal future, not your causal past. You can't catch up to them. You can't see them. They're gone. However, if someone fell in at nearly the same time as you, perhaps just seconds different, you might briefly see them. You might even communicate, though the tidal forces would make this difficult. If they fell in slightly before you and slightly ahead in the direction of the singularity, their image would be redshifted as their light fights its way back against the pull of gravity. If they fell in after you and are farther from the singularity, you might see them blue-shifted as their light gains energy falling toward you, but these encounters would be brief. The inexorable fall toward the singularity separates all objects inside the horizon. You might wonder if you could see light from the singularity itself or from regions near it. The answer is no, at least not with normal light. In the Schwarzschild geometry, the singularity is a point in your future. It's not a place you can look at. It's a time you're approaching. However, in a rotating Kerr black hole, the structure is different. The singularity is a ring, and there are regions of space-time inside the inner horizon where bizarre things happen. Theoretical paths exist where you could orbit inside the black hole, potentially even seeing light that's taken complex paths through the interior. Some solutions show closed time-like curves, paths through space-time that loop back on themselves, allowing time travel to your own past. These are mathematical artifacts of the Kerr solution, and most physicists believe they're not physically realizable. Quantum effects, or small perturbations, would probably destroy these exotic regions, replacing them with something more mundane, or more accurately, more unknown. One thing you would definitely observe is the increased tidal forces. As you fall, your body begins to feel stretched. Your feet are accelerating toward the singularity faster than your head. The difference in gravitational pull creates tension in your body. At first, this might feel like a gentle pulling sensation, like being stretched on a rack, but it grows exponentially. Within minutes, the forces exceed what bone and tissue can withstand. Fractures appear in your skeleton, your organs distort, blood flow becomes disrupted as vessels elongate and narrow. Your neural tissue stretches, disrupting the electrical signals that constitute your thoughts. Consciousness probably fails before complete physical disintegration, but the exact timing depends on how quickly the tidal forces grow, which depends on your distance from the singularity. In the final moments, you cease to be a person and become a stream of particles. Individual atoms are pulled apart, electrons are stripped from nuclei, protons and neutrons are torn into quarks and gluons. At the singularity, if general relativity is correct, even these fundamental particles are destroyed, crushed into infinite density. But again, we suspect that quantum gravity intervenes before this point. Perhaps particles tunnel into some other state. Perhaps they're converted into information on the event horizon. Perhaps they bounce off a quantum core and re-emerge as part of the Hawking radiation billions of years later. We simply don't know. Could you survive? Let's explore a hypothetical. Is there any possible way to survive falling into a black hole? Any technology, any physics we don't yet understand that might save you? The answer is almost certainly no, but let's examine the possibilities. First, could you avoid crossing the horizon in the first place? If you had a powerful enough rocket, you could hover just outside the event horizon, maintaining your position against the pull of gravity. The problem is the energy requirement. Near the event horizon, the gravitational pull approaches infinite. The thrust needed to hover becomes infinite. No conceivable rocket could generate this. Even if you had a matter-antimatter engine with perfect efficiency, converting 100% of your fuel into thrust, you couldn't do it. The math doesn't work. What about using the black hole itself for energy? The ergosphere, the region outside the event horizon of a rotating black hole where space is dragged around, allows a process called the Penrose process. You could throw an object into the ergosphere in a specific trajectory, such that when it splits, part falls into the black hole, while another part escapes with more energy than you started with. You've extracted energy from the black hole's rotation. An advanced civilization might build a massive apparatus around a black hole to harvest this energy, but this doesn't help you survive falling in. It just gives you power. Once you cross the horizon, no amount of power can bring you back. Could you use a wormhole? In certain solutions to Einstein's equations, black holes connect to white holes, hypothetical regions where matter and energy can only escape, never enter. The connection would be a wormhole, a tunnel through space-time. If you fell through a black hole, you might emerge from a white hole somewhere else, either in another part of our universe or in another universe entirely. This is appealing, and it's been the basis for countless science fiction stories. But there are severe problems. First, wormholes in general relativity are unstable. They collapse too quickly for anything to pass through. To keep them open, you'd need exotic matter with negative energy density. We have no evidence that such matter exists in sufficient quantities. Second, even if a wormhole existed, the tidal forces inside would still be lethal. You'd be spaghettified long before you emerged on the other side. Third, theoretical analysis suggests that the interior of a realistic black hole doesn't contain traversable wormholes. The mathematical solutions that allow them require perfect symmetry and specific conditions that are never met in nature. What about quantum tunneling? Quantum mechanics allows particles to tunnel through barriers they classically couldn't penetrate. Could your atoms quantum tunnel out of the black hole? The probability of this is unimaginably small. Quantum tunneling is effective over very short distances. distances comparable to atomic sizes. The event horizon might be millions of kilometers from the singularity. The probability of a single particle tunneling out is so close to zero that it's meaningless. The probability of all the particles that make up your body tunneling out simultaneously and reassembling correctly on the other side is far, far beyond impossible. It's not just unlikely. It violates basic principles of how quantum mechanics works at macroscopic scales. Could an advanced civilization save you? If there were beings with technology far beyond ours, could they reach into the black hole and pull you out? The problem is causality. Once you're inside the event horizon, you're causally disconnected from the outside universe. There's no way for signals to reach you from outside, and no way for you to send signals out. Even a civilization that could manipulate space-time itself would face this limit. General relativity isn't just a description of how things are, it's a statement about the structure of causality itself. Breaking these rules would require physics that we don't just not understand yet, physics that might be impossible in principle. The only remotely plausible way to survive would be if the interior of the black hole is radically different from what general relativity predicts. If quantum gravity creates a hard surface where the singularity should be, a surface you could land on without being destroyed, then maybe, just maybe, you could survive. But this surface would have to support you against the tidal forces, which are still enormous, and you'd be trapped forever, unable to communicate with or return to the outside universe. You'd exist in a pocket universe of your own, isolated from everything, with no way out. That's not survival in any meaningful sense. Black holes in different contexts. Not all black holes are created equal, and where you encounter one matters enormously. Let's consider different scenarios. If you fell into a stellar mass black hole, you'd be dead before you knew what happened. These black holes, formed from the collapse of massive stars, typically have masses between 3 and 20 times the Sun. Their event horizons are correspondingly small, just a few kilometers across. The tidal forces at the horizon are devastating. You'd be torn apart while still far outside, ripped into a stream of atoms that would then cross the horizon as a thin beam of particles. There's no story here because there's no time to experience anything. If you fell into an intermediate mass black hole, somewhere between 100 and 100,000 solar masses, the situation is better, but still fatal. You might survive to the horizon, but not long past it. The tidal forces would kill you within seconds to minutes of crossing. These black holes are rare and poorly understood. We're not even sure how they form. They might be the result of collisions between stellar mass black holes in dense star clusters, or they might be remnant seeds from the early universe that never grew to supermassive size. Supermassive black holes, as we've discussed, give you the most time. With millions to billions of solar masses and event horizons measured in millions of kilometers, the tidal forces at the horizon are weak enough that you could survive crossing. You'd have minutes to, perhaps hours inside, before tidal forces became lethal. This is long enough to observe, to think, to understand that you've passed the point of no return. Long enough for the experience to have meaning, however terrifying. Then there are primordial black holes, hypothetical objects that might have formed in the first moments after the Big Bang. These could have any mass, from far less than a gram to many thousands of solar masses. A tiny primordial black hole, with the mass of a mountain but the size of an atom, would have horrific tidal forces. You'd never get close. The radiation from its Hawking radiation would incinerate you. A large primordial black hole would behave like a stellar or supermassive hole depending on its size. But here's the interesting part. If primordial black holes exist, and if some are very small, they might be evaporating right now. The final moments of black hole evaporation are thought to be explosive. The last bit of mass is converted into a burst of high-energy particles and gamma rays. If a primordial black hole evaporated near you, the result would be like a nuclear explosion. But this is different from falling in. This is being nearby when a black hole dies. What about falling into Sagittarius A star, the black hole at the center of our galaxy? This is a supermassive black hole with 4 million solar masses. The event horizon is about 12 million kilometers in radius. The tidal forces at the horizon are comfortable by black hole standards. You'd cross alive. But there's a catch. Sagittarius A star is usually quiet, but it occasionally flares. If it's actively feeding when you fall in, the environment near the horizon would be filled with superheated plasma, intense magnetic fields, and lethal radiation. The gas forming an accretion disk around the hole reaches temperatures of millions of degrees. You'd be cooked long before tidal forces became a problem. For a survivable fall, at least past the horizon, you'd need a quiescent black hole, one that hasn't eaten recently. Now imagine falling into M87 star, the supermassive black hole at the center of the M87 galaxy. This is one of the most massive black holes known, containing 6.5 billion solar masses. The event horizon is roughly 19 billion kilometers across, larger than our entire solar system. The tidal forces at the horizon are incredibly weak. You could cross and not feel anything unusual for a long time. But M87 star is highly active. It's shooting a jet of plasma 5,000 light-years into space at nearly the speed of light. The magnetic fields near this black hole are unimaginably strong. The environment is violent. This isn't a peaceful place to fall. Unless you approached from a direction far from the jet and the accretion disk, you'd never survive long enough to cross the horizon. The mathematics of doom. Let's get technical for a moment and examine the actual mathematics that predicts your fate. The Schwarzschild metric describes the space-time around a non-rotating black hole. In coordinates, it looks like this. ds squared equals negative times 1 minus 2 gm over rc squared times dt squared plus 1 minus 2 gm over rc squared, inverse times dr squared plus r squared times d omega squared. This equation tells you how distances and times are measured in the curved spacetime around the black hole. The term 2 gm over c squared is called the Schwarzschild radius, and it's the radius of the event horizon. M is the mass of the black hole, g is Newton's gravitational constant, and c is the speed of light. Notice what happens at the Schwarzschild radius. The coefficient in front of dt squared becomes 0. Time, as measured by distant observers, stops. The coefficient in front of Dr. squared becomes infinite. Radial distance becomes infinitely stretched. This is the mathematical signature of the event horizon. It's a coordinate singularity, a place where the coordinates break down but the actual geometry might still be smooth. By changing to different coordinates, called Eddington-Finkelstein coordinates or Kruskal-Szekeres coordinates, you can describe what happens at the horizon from an infalling observer's perspective without the singularities. In Kruskal-Szekeres coordinates, the event horizon appears as a diagonal line on a spacetime diagram. The singularity appears as a hyperbola. All future-directed paths inside the horizon lead to the singularity. There's no path that goes sideways or backward. This is the geometric reason you can't escape. Inside the horizon, the direction toward the singularity is time-like. It's a direction in time, not space. Trying to avoid the singularity is like trying to avoid tomorrow. You can change how you get there, but you can't avoid arriving. The tidal forces can be calculated from the Riemann curvature tensor. For a Schwarzschild black hole, the radial tidal force experienced by an object of length L falling radially is proportional to gml over r cubed. Notice the r cubed in the denominator. The tidal force increases rapidly as you approach the singularity at r equals 0. For a supermassive black hole, at the event horizon, this force might only be a few times Earth's surface gravity per meter of height. Uncomfortable, but not immediately lethal. But as you fall inward, r decreases. At 1/10 the horizon radius, the force is 1,000 times larger. At 1/100th, it's 1,000,000 times larger. By the time you're close to the singularity, the forces are so large that they rip apart not just atoms but potentially even space-time itself. The time it takes to fall from the horizon to the singularity can be calculated from the geodesic equations. For a Schwarzschild black hole, if you fall radially inward from rest at the horizon, the proper time is pi times gm/c³. For our 10 million solar mass black hole, this works out to about 300 seconds, 5 minutes. This is a finite, calculable number. It's not an opinion or an estimate. It's a direct prediction of general relativity. Once you cross the horizon, you have a finite, deterministic amount of time left. For a Kerr black hole, the mathematics is more complex. The metric has additional terms that depend on the black hole's angular momentum. The event horizon is smaller than the Schwarzschild radius. There's an ergosphere outside the horizon. Inside, there's an inner horizon and a ring singularity. The geodesics, the paths that objects follow, can be far more complicated. Some paths spiral around the ring singularity multiple times before hitting it. Some paths, in the idealized mathematical solution, pass through the ring and emerge into other regions of space-time. But these exotic paths are probably not physically real. Small perturbations would destroy the inner horizon, replacing it with a chaotic region where the curvature becomes irregular and unpredictable. The take-home message from the mathematics is this: the predictions are not speculative, they're as solid as any prediction in physics. If general relativity is correct in the regime where we've tested it, and we have every reason to believe it is, then these predictions about black holes follow inevitably. The only uncertainty comes at the singularity itself, where the theory breaks down and quantum gravity must take over. But the existence of the event horizon, the fact that crossing it is irreversible, the inexorable fall toward the singularity, these are not in doubt. Observational evidence. You might wonder whether any of this is real. Black holes are theoretical predictions, but do they actually exist? The evidence is now overwhelming. We've observed stars orbiting invisible compact objects at the centers of galaxies. The orbits obey Kepler's laws exactly, allowing us to calculate the mass of the central object. For Sagittarius A star, the mass is 4 million suns, concentrated in a region smaller than Mercury's orbit. There's no known object other than a black hole that could be this massive and this compact. We've detected gravitational waves from merging black holes. The LIGO and Virgo detectors have observed dozens of these events. The waveforms match precisely what general relativity predicts for two black holes spiraling together and merging. The masses are consistent with stellar mass black holes, typically tens of solar masses each. The final merged black hole rings down, settling into a stable Kerr solution exactly as the theory predicts. We've even observed mergers, where the mass of the final black hole is less than the sum of the initial masses. The missing mass was radiated away as gravitational waves, energy carried off in ripples of space-time itself. We measured it. We detected the energy. The agreement between theory and observation is stunning. We've photographed black holes. The Event Horizon Telescope imaged M87 star in 2019 and Sagittarius A star in 2022. The images show a bright ring surrounding a dark center, exactly what models predict. The size of the dark region matches the event horizon predicted by general relativity. The asymmetry in brightness around the ring matches models of rotating black holes with accretion disks. These aren't indirect measurements. These are pictures. We've seen the shadow of an event horizon. We've observed X-ray binaries, where a visible star orbits a compact object, and the compact object is accreting matter from the star. The matter spirals inward, heats up, and radiates X-rays before crossing the event horizon. The X-ray spectrum and variability match models of accretion onto black holes. There's a specific signature called a power law spectrum with an exponential cutoff that's characteristic of matter heated to extreme temperatures very close to an event horizon. We've seen this signature in dozens of systems. So yes, black holes are real. They exist in nature. The predictions of general relativity have been tested and confirmed in every regime where we can observe them. The one regime we can't observe is the interior, past the event horizon. That remains theoretical. but given how well the theory works everywhere else, there's every reason to believe it's correct there too. The final moments. Let's return one last time to your subjective experience. You've been falling for several minutes now. The tidal forces are growing. You can feel your body stretching, your bones ache, your vision begins to distort as your eyeballs elongate. You try to look back at the universe you came from, but the view has compressed into a tiny bright spot, impossibly distant. You try to look forward, toward the singularity, but there's only darkness. Your thoughts become fragmented as the neural tissue in your brain stretches and tears. Consciousness, that mysterious property that made you who you were, begins to fade. In these final moments, you might wonder what it all means. Is there any purpose to this experience? Any lesson to be learned? The physics is clear. You will be destroyed. Your atoms will be torn apart. The information that constituted you might be preserved in some abstract quantum mechanical sense, encoded on the horizon and released in Hawking radiation over timescales longer than the current age of the universe. But you, the person, the consciousness, the collection of memories and hopes and fears, you are ending. There is no afterlife inside a black hole. There is only termination. Yet there's something profound in this destruction. You're experiencing something no human has ever experienced, and likely never will. You're testing the limits of physical law. You're falling into a realm where the rules of reality are different, where space and time trade places, where the future is a place and the past is a direction. You're one of the few objects in the universe to cross this ultimate boundary and see, even briefly, what lies beyond. Your destruction is total, but your journey is unique. Physicists who study black holes often speak of them with a mixture of awe and terror. They're the most extreme objects the laws of physics allow. They're regions where gravity wins absolutely, where the universe creates a boundary that cannot be crossed in reverse, where time itself ends. They're natural laboratories for testing our deepest theories about the nature of reality. And they're ultimately unknowable from the outside. We can measure their mass, their spin, their charge, but we can never see inside. We can never know what happens at the singularity. We can only calculate and infer and wonder. If you could somehow send a message back from inside the event horizon, what would you say? The question is meaningless. No message can escape. Light cannot travel outward from inside the horizon. Radio waves cannot penetrate. Gravitational waves cannot propagate backward in time. You are causally disconnected from the universe you came from. Anything you think, anything you feel, any last words or profound insights, they die with you. The universe will never know. This is perhaps the most unsettling aspect of black holes. They're not just destructive, they're erasing. They remove information from the observable universe. Everything that falls in contributes to the mass, spin, and charge of the whole, but all other details are lost. It doesn't matter if what fell in was a hydrogen atom or a Shakespeare sonnet or a human consciousness. The black hole grows by the same amount. The exterior appearance is identical. This is summarized in the physicist John Wheeler's phrase, "Black holes have no hair." They're characterized completely by just three numbers: mass, angular momentum, and charge. Everything else is gone, or is it? The information paradox suggests that maybe, just maybe, the information is preserved in subtle quantum correlations. Maybe the universe doesn't really lose anything. Maybe you're not truly erased, but transformed into something else, something that exists in a form we don't yet understand. This is the hope that drives much of modern theoretical physics. The hope that reality is fundamentally lawful, that information is conserved, that even in the most extreme environments, the universe makes sense. Conclusion. The abyss stares back. What if you fell into a black hole? You'd die. Not immediately, not if the black hole is large enough, but inevitably. You'd experience time dilation, seeing the outside universe speed up. You'd cross the event horizon without feeling a sudden change. You'd have minutes, maybe hours, if the black hole is extremely massive, before tidal forces tore you apart. You'd see strange optical effects as light bent around you in extreme ways. You'd fall inexorably toward a singularity where physics as we know it breaks down. And then you'd cease to exist, your atoms scattered, your information perhaps encoded on the horizon, but you, the person, gone forever. This is what physics predicts. This is what the mathematics shows. This is what happens when you fall into a black hole. It's terrifying in its finality. There are no escape hatches, no clever tricks, no last-minute reprieves. Once you cross the horizon, your fate is sealed. You will be destroyed. The only variables are the timescale and the details of your disintegration. But there's something beautiful in this horror. Black holes are testaments to the power of mathematics to predict reality. They were predicted by theory decades before we had any observational evidence they existed. Carl Schwarzschild found the first solution in 1916, just months after Einstein published general relativity. For decades, physicists debated whether these solutions represented real objects or mathematical curiosities. The debate is over. Black holes are real. The theory was right. They're also reminders of how much we don't know. The interior of a black hole is a mystery. The singularity is a sign that our theories are incomplete. Quantum gravity, when we finally understand it, will tell us what really happens at the center. It might tell us that singularities don't exist, that there's something else there, something we can't yet imagine. Or it might confirm that the singularity is real, that there are points in space-time where reality truly ends. Black holes sit at the intersection of the very large and the very small. They're macroscopic objects, some with masses of billions of suns that nonetheless require quantum mechanics to fully understand. They're bridges between general relativity and quantum field theory, between our theory of gravity and our theory of particles. They're natural laboratories where these theories meet, and where we discover that they don't quite fit together. Solving the puzzles they present might lead to a unified theory of physics, a single framework that describes everything from subatomic particles to the structure of the universe itself. If you fell into a black hole, you'd be participating, however involuntarily, in one of the universe's deepest mysteries. Your destruction would be final, but meaningful. You'd be testing the limits of reality itself. And though you couldn't report back, though your experience would die with you, the fact of your fall would be recorded in the increased mass of the black hole, a tiny increment in its event horizon radius, a minuscule change in the curvature of space-time around it. You'd become part of the black hole, merged into its structure, as permanent as anything in the universe can be. Until, trillions of years from now, the black hole itself evaporates through Hawking radiation. At that point, the information about your quantum state, scrambled beyond recognition, would be released back into the universe. In some sense, you'd return. Not as a person, not even as atoms, but as quantum correlations in a sea of particles spreading through empty space. It's not immortality, it's not preservation, but it's not quite destruction either. It's transformation into something so different that we barely have language to describe it. This is what happens when you fall into a black hole. The answer is physical, mathematical, and philosophical all at once. It's a journey to the edge of what we know, and past it. It's an encounter with the most extreme environment the universe creates. It's a one-way trip into the unknown, a fall into darkness from which there is no return. It's the ultimate fate of anything that crosses that invisible line in space, where escape velocity exceeds light speed, where time and space trade roles, where the future becomes a place and the past becomes a direction. It's death, certainly, but it's also something more. It's the universe showing us what it can do when it pushes the laws of physics to their absolute limit. And it's terrifying. If you somehow found yourself approaching a black hole, falling toward that point of no return, you'd have time to think, time to wonder, time to feel the tidal forces slowly growing, stretching you thin, pulling you apart molecule by molecule, time to watch the universe outside compress into a shrinking point of brilliant light, time to see the darkness ahead, the absence of everything, the place where space-time ends. And in those final moments, you might understand something profound about the nature of reality. Not a specific fact or equation, but a feeling. The feeling of being utterly subject to forces beyond your control. The feeling of being torn apart by the fabric of space-time itself. The feeling of approaching a boundary that cannot be crossed in reverse. The feeling of ending. This is what awaits inside a black hole. This is where curiosity leads if you push it too far. This is the price of exploring the universe's most extreme regions. We send our telescopes and our theories to study these objects. We observe them from a distance, safe in our laboratories and observatories, billions of miles or billions of light years away. We calculate and model and predict, but we never touch them. We never cross that line, because to do so would be to accept annihilation. Complete, total, irreversible annihilation. Black holes are nature's guillotines. They're executioners built from pure geometry. They're the universe's way of saying there are places you cannot go and return from. There are regions of space-time that are forbidden to exit. There are boundaries that, once crossed, lead only to termination. They're walls at the edge of the possible, beyond which lies not another country but the end of all countries. Not another universe, but the end of this one. Not another reality, but the cessation of reality as you can experience it. And yet, they're also the most fascinating objects in the cosmos. They're elegant in their simplicity. Defined by just 3 numbers, they're profound in their implications, touching on everything from thermodynamics to information theory to the nature of time. They're beautiful in their mathematics. Exact solutions to Einstein's equations, perfect geometries emerging from abstract principles. They're the universe at its most extreme and its most pure. So if you fell into a black hole, what would happen? You'd experience the most extreme physics the universe allows. You'd see time and space do things that no human has ever witnessed. You'd cross a boundary that separates the knowable from the unknowable. You'd fall toward a point where all of physics breaks down, and you'd die, completely and irreversibly, torn apart by tidal forces that grow without limit until even your atoms are ripped into their constituent particles. This is not speculation. This is not guesswork. This is what the mathematics predicts, what the theory requires, what the universe does when you fall into a black hole. The question isn't really what if. The question is when. When will we understand the interior well enough to know what really happens at the singularity? When will quantum gravity give us a complete picture of what lies beyond the event horizon? When will we solve the information paradox and understand how black holes preserve or destroy information? These questions remain open. The interior of a black hole remains the greatest mystery in physics. And until we solve it, until we understand what really happens when you fall past the point of no return, we'll continue to wonder, to calculate, and to fear the abyss that stares back at us from the heart of every black hole in the universe. What if you fell into a black hole? The answer is more complex than a simple death sentence. Let's explore even deeper into the physics, the alternatives, and the cosmic implications of these mysterious objects. The thermodynamics of black holes. Black holes aren't just gravitational prisons. They're thermodynamic objects with temperature, entropy, and the ability to radiate. This realization, which came from Stephen Hawking's work in the 1970 seconds, fundamentally changed how we think about black holes. Before Hawking, black holes were thought to be perfectly black, absorbing everything and emitting nothing. Hawking showed that quantum effects near the event horizon cause black holes to glow with thermal radiation. The temperature is incredibly low, inversely proportional to the mass. For a solar mass black hole, the temperature is about 60 nanokelvins, far colder than the cosmic microwave background. The black hole absorbs more energy from the background radiation than it emits, so it grows. But for very small black holes, the temperature can be substantial. Here's where it gets interesting. As a black hole radiates, it loses mass. As it loses mass, its temperature increases. As the temperature increases, it radiates faster. This creates a runaway process. A black hole doesn't evaporate at a constant rate. It accelerates. The final moments of evaporation happen in a violent burst of energy. For a solar mass black hole, the evaporation time is about 10 to the 67 years, far longer than the current age of the universe. For a supermassive black hole, it's even longer, 10 to the 100 years or more. But for a small primordial black hole, perhaps one with the mass of a mountain, the evaporation time might only be 13.8 billion years, roughly the age of the universe. These black holes, if they existed, would be exploding right now, somewhere in the universe. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is strange. For normal objects, entropy is extensive. It scales with volume. But for black holes, it scales with surface area. This observation led to the holographic principle, the idea that the information content of a region of space might be encoded on its boundary rather than in its interior. If true, this principle applies not just to black holes, but to the entire universe. It suggests that our three-dimensional reality might be a projection of information encoded on a two-dimensional surface at the edge of the cosmos. This is one of the most profound ideas to emerge from black hole physics, and it has implications far beyond the question of what happens when you fall in. The laws of black hole thermodynamics parallel the laws of ordinary thermodynamics in eerie ways. The first law relates changes in mass to changes in area, rotation, and charge, analogous to the first law relating changes in energy to work and heat. The second law states that the total entropy, including black hole entropy, never decreases, analogous to the thermodynamics second law. The third law says you can't reduce a black hole's temperature to absolute zero in a finite number of steps, analogous to the thermodynamic third law. These parallels aren't coincidences. They suggest a deep connection between gravity and thermodynamics, between the geometry of space-time and the behavior of matter and energy. If black holes are thermodynamic objects, they must have microstates, specific quantum configurations that correspond to their macroscopic properties. For an ordinary gas, the entropy counts the number of possible arrangements of molecules that give the same temperature and pressure. For a black hole, what are the microstates? String theory offers one answer. In string theory, black holes can be modeled as bound states of fundamental strings and branes. By counting these states, physicists have successfully reproduced the Bekenstein-Hawking entropy formula for certain types of black holes. This is one of the major successes of string theory, a concrete calculation that matches a prediction of general relativity using completely different methods. What does this mean for you as you fall in? If the holographic principle is correct, the information about your quantum state isn't destroyed. It's encoded on the event horizon as you cross it. The horizon gains area proportional to your entropy. Over time, this information is released in the Hawking radiation through incredibly complex quantum correlations. You're not preserved in any recognizable form. Your consciousness is gone. Your body is destroyed. But the information that specified your exact quantum state, every particle, every field, every degree of freedom, survives in principle. It's scrambled beyond any practical recovery, but it exists. This doesn't make your death any less final from a subjective perspective, but it means the universe doesn't lose information. Quantum mechanics remains unitary. The laws of physics remain consistent. Comparing cosmic extremes. To truly appreciate what falling into a black hole means, it helps to compare it to other extreme environments in the universe. Let's start with neutron stars, the closest relatives of black holes. A neutron star is what you get when a massive star collapses but doesn't quite have enough mass to form a black hole. The result is an object about 20 kilometers across, containing 1 to 2 solar masses. The density is similar to an atomic nucleus. A teaspoon of neutron star material would weigh about 1 billion tons. The gravity at the surface is intense, about 100 billion times Earth's gravity. If you fell onto a neutron star, you'd be moving at a significant fraction of light speed when you hit. The impact would convert your kinetic energy into heat, vaporizing you instantly. But here's the key difference from a black hole. You hit a surface. There's something there to stop you. It kills you, but it's a boundary you can interact with. Black holes have no surface. The event horizon isn't a physical barrier. If you fell into a black hole and a neutron star of similar mass from the same starting distance, the gravitational acceleration would be similar for most of the journey. But at the end, the neutron star gives you a surface to crash into, while the black hole offers only a continued fall toward a singularity. The neutron star has a finite density. The black hole's singularity has infinite density. The neutron star can support itself against gravity through neutron degeneracy pressure. The black hole has collapsed past the point where any known force can resist gravity. Now, consider the early universe. At the moment of the Big Bang, or rather a tiny fraction of a second after it, the entire observable universe was compressed into a region smaller than an atom. The density was enormous, far exceeding even nuclear density. The temperature was around 10 to the 32 Kelvin. At these temperatures, the familiar particles we know couldn't exist. Even protons and neutrons were broken down into quarks and gluons. This quark-gluon plasma filled all of space. In some ways, the early universe resembled the interior of a black hole, a region where density and temperature are extreme, where the normal rules don't apply. But there's a crucial difference. The early universe was expanding. Everything was moving apart. In a black hole, everything is moving together, falling toward the singularity. Some cosmologists have suggested that the entire observable universe might be the interior of a black hole in a larger parent universe. In this scenario, what we call the Big Bang was the event horizon crossing. We're living inside the black hole, falling toward a singularity that lies not in our past but in our future. The expansion of the universe, in this model, is the natural evolution of the interior geometry. This idea is speculative and controversial. It makes predictions that are hard to test, but it illustrates how the physics of black holes might be connected to cosmology, how the very large and the very small might be linked through extreme gravity. Let's compare falling into a black hole with falling into other cosmic structures. If you fell into the sun, you'd burn up in the outer atmosphere, the corona, where temperatures reach millions of degrees. Your atoms would be ionized, stripped of electrons, long before you reach the visible surface. If you fell into a gas giant like Jupiter, you'd be crushed by atmospheric pressure. At a depth of a few thousand kilometers, the pressure exceeds what any material can withstand. Your body would be compressed and heated until it dissolved into the surrounding hydrogen and helium. If you fell into a white dwarf, a dense stellar remnant held up by electron degeneracy pressure, you'd hit the surface at tremendous speed. The impact would release energy equivalent to a nuclear explosion. In all these cases, there's something to interact with. Matter, pressure, heat, a surface. In a black hole, there's nothing until you reach the singularity. You fall through vacuum, through empty, curved space, with nothing to slow you down. The tidal forces grow, but they're not from colliding with anything. They're from the geometry of space-time itself. This makes black holes unique. They're the only objects where the danger comes purely from gravity, from the curvature of space and time, with no contribution from matter or radiation until you're already doomed. The black hole's role in galactic evolution. Black holes aren't just cosmic curiosities. They play a crucial role in how galaxies form and evolve. Every large galaxy has a supermassive black hole at its center. The mass of this black hole is tightly correlated with the mass of the galaxy's central bulge, the dense spherical region of old stars surrounding the galactic core. This correlation, called the M-sigma relation, suggests that black holes and galaxies grow together. But how? Black holes contain less than 1% of a galaxy's mass. How can such a small component influence something so much larger? The answer is energy. When a black hole feeds, it releases enormous amounts of energy. Matter falling toward the event horizon forms an accretion disk where it heats to millions of degrees. This hot gas radiates across the electromagnetic spectrum. In the most active phases, a supermassive black hole can outshine its entire host galaxy. Quasars, the brightest sustained objects in the universe, are powered by supermassive black holes consuming matter at prodigious rates. A single quasar can emit as much energy as 1,000 galaxies. This energy has consequences. It heats the surrounding gas, driving powerful winds that blow material out of the galaxy's core. It prevents the gas from cooling and forming stars. It can even shut down star formation in the entire galaxy. This process is called AGN feedback, where AGN stands for active galactic nucleus. It's one of the most important mechanisms in modern theories of galaxy formation. Without it, simulations produce galaxies that are too massive, too blue, too full of young stars. With it, the simulations match observations. The black hole acts as a thermostat. When too much gas falls toward the center, the black hole becomes active, heats the gas, and drives it out. Star formation slows. The black hole starves and becomes quiescent. Eventually, gas cools and falls back in, and the cycle repeats. Over billions of years, this self-regulating feedback shapes the galaxy's structure and evolution. If you fell into a black hole during an active phase, you'd be traversing one of the most energetic environments in the universe. The accretion disk would be glowing with X-rays. The magnetic fields would be twisted into complex structures. Jets of plasma might be shooting out perpendicular to the disk at nearly light speed. The radiation pressure would be intense. If you approached too close to the disk, you'd be heated and ionized long before tidal forces became a problem. This is why active black holes are even more dangerous than quiescent ones. The black hole itself is deadly, but the environment around it can kill you just as effectively. Black holes also influence their surroundings through purely gravitational effects. Stars near the galactic center orbit the black hole at high speeds. Some pass close enough that tidal forces from the black hole can tear them apart, creating what's called a tidal disruption event. The stellar debris forms a temporary accretion disk, causing a bright flare that can last for months or years. These events are rare for any given galaxy, happening perhaps once every 10,000 years, but they're powerful diagnostic tools. By observing how the star is torn apart and how the debris evolves, astronomers can measure the black hole's mass and spin. There's also the possibility of gravitational slingshots. A star or planet passing close to a supermassive black hole can be accelerated to extreme velocities, potentially reaching speeds high enough to escape the galaxy entirely. These hypervelocity stars have been observed streaming through intergalactic space. They're evidence of close encounters with black holes, cosmic game of billiards played with stellar masses. If you were in a spacecraft near a black hole, you could use this effect intentionally, performing a gravitational assist to change your trajectory. But the margins are razor thin. Get too close, and you cross the event horizon. Stay too far, and the assist is negligible. The window for a successful slingshot is narrow, and the penalties for error are absolute. Alternative theories and exotic possibilities. General relativity has passed every test we've thrown at it, but that doesn't mean it's the final word. Several alternative theories of gravity make different predictions about black holes. Some of these alternatives might change what happens when you fall in. Let's explore a few. First, there's modified Newtonian dynamics, or MOND, which attempts to explain galaxy rotation curves without dark matter by modifying the laws of gravity at low accelerations. MOND doesn't really address black holes directly. It's focused on different phenomena, but it reminds us that gravity might not behave exactly as general relativity predicts in all regimes. More relevant are theories that modify general relativity at high curvatures or short distances. Loop quantum gravity, for instance, suggests that space and time are quantized at the Planck scale. Instead of smooth geometry, space-time is made of discrete units. In this framework, The singularity at the center of a black hole might be replaced by a bounce. Matter falling in would reach a point of maximum density and then rebound, potentially creating a new expanding region of space-time. From the outside, it's still a black hole. But from the inside, the singularity is avoided. You'd still die from tidal forces, but not because you hit a singularity. Instead, you'd be torn apart by extreme but finite curvatures. String theory offers another perspective. In string theory, black holes can be modeled as bound states of strings and branes. The horizon is a real physical surface made of these objects. What appears from far away as smooth, empty space is actually a dense configuration of fundamental constituents. Some versions of string theory predict that small black holes might decay into other objects, bypassing the evaporation process. Large black holes still evaporate through Hawking radiation, but the final stages might be different. Instead of a violent explosion, the black hole might transform into a stable remnant, a Planck mass object that doesn't radiate further. There are also theories involving extra dimensions. In models with large extra dimensions, gravity can leak out of our familiar three-dimensional space into the extra dimensions. Near a black hole, where gravity is extreme, these effects might become noticeable. The event horizon might have structure in the extra dimensions. There might be ways to escape using these extra degrees of freedom, though this remains highly speculative. If extra dimensions exist and are accessible near black holes, the interior geometry could be far more complex than general relativity predicts. One exotic possibility involves the firewall hypothesis we mentioned earlier. This idea comes from trying to resolve the information paradox. It suggests that the event horizon isn't a smooth surface, but a region of enormous energy density. Any observer trying to cross would be incinerated instantly. This contradicts the equivalence principle, which says that freely falling observers shouldn't experience anything unusual at the horizon. If the firewall is real, then the question of what happens when you fall into a black hole has a simple answer. You vaporize at the horizon. You never make it inside. But most physicists are skeptical of firewalls. They seem to require giving up too much of general relativity's elegant structure to save quantum mechanics. Another idea is that black holes might not have event horizons at all, but instead have surfaces that are almost but not quite at the critical radius. These objects are called black hole mimics, or horizonless compact objects. They'd look almost identical to black holes from a distance. They'd have strong gravitational fields. They might even have almost the same gravitational wave signatures when they merge. But they wouldn't have the information-destroying properties of true black holes. Matter falling in would hit a surface, bounce, and potentially escape. There'd be no singularity, no loss of information, no irreversible crossing of a boundary. Evidence for such objects is weak. Observations strongly favor standard black holes. But the possibility remains that nature might have found a way to avoid the most extreme predictions of general relativity. There's also the fuzzball proposal from string theory. This suggests that what we think of as the interior of a black hole doesn't exist. Instead, the black hole is a highly excited string state that fills the entire region up to the horizon. There's no empty space inside, no smooth geometry, just a complex configuration of strings in a highly quantum state. If you fell in, you'd merge with this configuration. Your information would be preserved, encoded in the string state, but you as a person would be gone, dissolved into the collective quantum state of the fuzzball. All of these alternatives are attempts to resolve the paradoxes and infinities that plague black holes in classical general relativity. They share a common theme: the idea that quantum gravity, whatever it turns out to be, will modify the structure of black holes in ways that avoid the most extreme predictions. Singularities might not be real. Horizons might be fuzzy or firewall-like rather than smooth. The interior might not exist as a classical space-time region, but none of these alternatives offer you a way to survive. At best, they change how you die, but the outcome is the same. You enter you're destroyed, and you don't come back. The experience of time inside the horizon. Let's return to the subjective experience, focusing specifically on time. Time inside a black hole behaves in ways that are deeply counterintuitive. Outside the horizon, time flows forward. You have a past and a future. You can make choices that affect what happens next. Inside the horizon, the direction toward the singularity becomes time-like. It's literally a direction in time, not space. You can no more avoid moving toward the singularity than you can avoid moving forward in time outside the horizon. This isn't just a metaphor. The mathematical structure of space-time inside the horizon makes the singularity your future. What does this mean experientially? Imagine you're inside, falling toward the center. You look around. Space appears to extend in different directions. You can turn your head, rotate your body. But one direction, the direction toward the singularity, is fundamentally different. It's not that you're being pulled in that direction by a force, though tidal forces certainly exist. It's that moving forward in time means moving in that spatial direction. The passage of time carries you toward the singularity automatically. This is related to a property called geodesic incompleteness. A geodesic is the path a freely falling object follows through curved space-time. Outside the black hole, geodesics extend infinitely into the future. You can keep falling forever if nothing stops you. Inside the horizon, geodesics that point toward the singularity have finite length. They end. Time itself ends at the singularity. This isn't because you hit something. It's because the space-time geometry becomes singular. The metric, the mathematical object that defines distances and times, diverges. Time stops, having meaning. From a mathematical perspective, the singularity is a boundary of space-time. It's not a point or surface within space-time. It's an edge. Asking what happens after you reach the singularity is like asking what's north of the North Pole. The question doesn't make sense because you've reached the boundary of the manifold. There is no after. There's no before in the usual sense either, because time near the singularity is so distorted that the usual concepts of earlier and later break down. Some physicists have explored whether you might perceive time differently as you approach the singularity. Would time seem to slow down from your perspective? Would you experience a finite duration that feels like an eternity? The calculations suggest not. Your proper time, the time measured by a clock you carry, ticks normally. You experience a finite number of seconds or minutes. They don't stretch out, they don't feel slow. From your perspective, time passes at 1 second per second all the way until the tidal forces destroy you or you reach the singularity, whichever comes first. But here's something strange. While you're inside the horizon, signals from other objects inside can reach you in complex ways. Light emitted by something closer to the singularity than you can travel outward and hit you. You can see things that fell in before you did, at least briefly, but you can never catch up to them. They're always ahead of you temporally. The light you see is from their past, and by the time you see it, they're even closer to the singularity or already destroyed. The interior of a black hole is causally connected in bizarre ways. The singularity is in the future of all interior points. Every point inside can send signals to every other point under the right conditions. But the overall structure still funnels everything toward the inevitable end. There's a concept called the stretched horizon, which is a time-like surface just outside the event horizon where, from the perspective of outside observers, everything that falls in appears to accumulate. From the outside, the black hole looks like a hot, dense surface that absorbs and scrambles information. From the inside, you pass smoothly through the horizon and continue falling. These two descriptions seem contradictory, but they're both correct in their respective reference frames. This is black hole complementarity, the idea that what happens at the horizon depends on your perspective. To an outside observer, you never cross. You're absorbed into the stretched horizon. To you, you cross smoothly and continue falling. Both descriptions are true, and they don't contradict each other, because no single observer can verify both simultaneously. This might be the strangest aspect of black holes. The reality of what happens depends on the observer. There's no objective fact about whether you cross the horizon. From the outside, you don't. From your perspective, you do. General relativity allows this because it's a theory about how space-time looks from different perspectives. There's no God's eye view, no objective reference frame. Every observer has their own experience of space-time, and all these experiences are valid. The black hole accommodates all of them simultaneously, each observer getting a consistent but different story. Black holes and the fate of information. Let's go deeper into the information paradox, because it's central to understanding what happens when you fall in. Information, in the quantum mechanical sense, refers to the complete specification of a quantum state. For a single particle, this includes its position, momentum, spin, and all other quantum numbers. For a system of many particles, it's the wave function or density matrix that describes all possible states and their probabilities. Quantum mechanics is deterministic at the level of the wave function. Given the state now, you can calculate the state at any future time. This process is unitary, meaning it preserves information. The total amount of information in a closed system never changes. Black holes seem to violate this. When you fall in, you take your information with you. From the outside perspective, that information is lost. It's behind the horizon, inaccessible. When the black hole eventually evaporates through Hawking radiation, the information should come out, but early calculations suggested it doesn't. The radiation is thermal, containing no information about what fell in. This is the paradox. Either information is destroyed, violating quantum mechanics, or it escapes, requiring mechanisms we don't understand. The resolution likely involves understanding that Hawking radiation isn't exactly thermal. It has subtle correlations that encode information. To see these correlations, you'd need to collect enormous amounts of radiation and perform quantum measurements on all of it simultaneously. This is far beyond any practical experiment, but in principle, the information is there. The black hole doesn't destroy it. It scrambles it into the outgoing radiation in an incredibly complex way. But here's the puzzle. The information about what fell in must start coming out in the Hawking radiation at some point. But when? If it comes out early, before the black hole has evaporated much, then it must come from near the horizon. But the horizon is supposed to be smooth. An observer falling through shouldn't encounter any information-carrying structure. If the information comes out late, after the black hole has largely evaporated, then it was stored inside for a long time. But where? The interior is falling toward the singularity. How does information make it from the interior back out to the horizon and then out in the radiation? Recent work suggests that the information starts coming out at a specific time, called the page time, which is when the black hole has evaporated about half its mass. Before the page time, the radiation is mostly thermal and entangled with the black hole interior. After the page time, the radiation becomes entangled with earlier radiation rather than with the interior. This transition requires the radiation to have very specific correlations. It might require that what we think of as separate degrees of freedom inside and outside the horizon are actually the same degrees of freedom described in different ways. This is the essence of black hole complementarity. If you could somehow measure these correlations in the Hawking radiation, you could, in principle, reconstruct the quantum state of everything that ever fell into the black hole. This includes you. Every particle in your body, every quantum state, every bit of information about your configuration would eventually emerge in the radiation. It wouldn't be you in any meaningful sense. It would be information that, if decoded perfectly, would allow someone to determine that an object with your specific quantum state once fell in billions of years ago. It's not resurrection. It's not even memory. It's just information preservation at the most fundamental level. This raises philosophical questions. If the information about you is preserved, but in a form that's completely unrecognizable, that's scattered across trillions of particles of radiation spanning light years of space, that would take a quantum computer the size of a galaxy to decode. In what sense is it preservation? From a physics standpoint, it means quantum mechanics remains unitary. The universe doesn't lose information, but from a human standpoint, it's meaningless. You're still destroyed. Your consciousness is still ended. The fact that information about your quantum state eventually escapes doesn't help you. The multiverse connection. Some interpretations of quantum mechanics suggest that when quantum measurements occur, the universe splits into multiple branches, each representing a different outcome. This is the many worlds interpretation. If it's correct, what happens when you fall? Into a black hole? Do you split into multiple versions? In some branches, do you somehow survive? The answer is almost certainly no. The many worlds interpretation doesn't create miraculous escapes from deterministic physical processes. If the laws of physics in your branch say you're destroyed, then you're destroyed in that branch. Other branches might have versions of you that didn't fall in, that made different choices. But the version of you that crosses the horizon is doomed regardless of interpretation. However, black holes might connect to the multiverse in a different way. Some theories suggest that the interior of a black hole could connect to another universe. This is the Einstein-Rosen bridge, a wormhole linking two separate space-time regions. In the simplest case, the other end is a white hole, a theoretical time-reversed version of a black hole where matter and energy can only exit, never enter. You'd fall into the black hole, pass through the wormhole, and emerge from the white hole in another universe. This sounds like an escape route, but there are massive problems. First, the connection is unstable. The wormhole collapses faster than light can cross it. To keep it open, you'd need exotic matter with negative energy density threaded through the throat. We have no evidence such matter exists in the necessary quantities. Second, the tidal forces inside the wormhole would be lethal. You'd be spaghettified long before emerging on the other side. Third, even if you could somehow survive and traverse the wormhole, you'd emerge into a universe that might have completely different physical laws, different constants of nature, potentially no atoms, no light, no structure. Survival in such a universe would be impossible. But let's entertain the possibility. Let's say you fall into a black hole that happens to contain a traversable wormhole held open by some exotic physics we don't understand. You pass through, experiencing intense tidal forces but somehow remaining intact. You emerge into another universe. What do you see? If the other universe is like ours, you'd see stars, galaxies, perhaps even planets. You'd be moving at high speed, carrying the kinetic energy from your fall. You'd need to slow down somehow, dissipate that energy without burning up. If you managed all this, you'd be stranded. There's no going back. The wormhole is one way. You're in a different universe with no connection to the one you came from. More likely, the other universe would be fundamentally different. Maybe it's earlier in its evolution, still opaque with hot plasma. Or maybe it's far older, cold and dark with all stars long dead. Maybe the constants of nature are different, and atoms are unstable. Maybe space-time has different dimensions, and your three-dimensional body can't exist there. The possibilities are endless, and almost all of them are lethal. The wormhole idea is fascinating theoretically, but as a survival mechanism, it's not promising. There's also the simulation hypothesis to consider. If our universe is a simulation running on some substrate outside our space-time, what happens when you fall into a black hole might depend on how the simulation handles it. Maybe the interior isn't simulated in detail. Maybe you simply stop being rendered once you cross the horizon. Maybe your consciousness is saved to a backup and reinitialized elsewhere. These ideas aren't physics in the traditional sense. They're speculation about the nature of reality itself. But they illustrate that the question, what happens when you fall into a black hole, might have answers that go beyond general relativity and quantum mechanics. Learning from black holes. Despite their dangers, black holes are invaluable to physics. They're natural laboratories for testing theories in regimes we can't access any other way. The extreme gravity near a black hole creates conditions where general relativity must be accurate. the quantum effects at the Horizon Probe, the intersection of quantum mechanics and gravity. The information paradox forces us to think deeply about the nature of quantum information. Black holes have driven theoretical physics forward for decades. They've also taught us humility. Before general relativity, we thought we understood gravity. Newton's law had worked perfectly for centuries. Then Einstein showed that gravity is curvature of space-time, and suddenly black holes became possible. Before quantum mechanics, we thought we understood matter. Classical physics seemed complete. Then quantum theory revealed a world of probabilities and uncertainties, and black holes became thermodynamic objects. Each time we think we understand, black holes reveal new mysteries. The recent detections of gravitational waves from merging black holes have opened a new window on the universe. These waves carry information about the black hole's masses, spins, and the dynamics of the merger. By analyzing the waveforms, we can test whether black holes behave as general relativity predicts. So far, they do, with stunning precision. But future observations might reveal deviations, hints of new physics, signatures of quantum gravity, or exotic matter. Black holes are no longer just theoretical constructs, they're observational targets. The Event Horizon Telescope images of M87 star and Sagittarius A star showed us the shadow of an event horizon, the photon ring, the structure of the accretion flow. Future observations with more telescopes and better resolution might reveal even more. We might see hotspots orbiting close to the horizon. We might measure frame dragging directly. We might observe flares and jets launching in real time. Each observation tests general relativity in stronger fields and teaches us about the extreme physics near the event horizon. For future civilizations, if humanity survives and expands through the galaxy, black holes might become resources. A rotating black hole contains enormous amounts of rotational energy accessible through the Penrose process. An advanced civilization could harvest this energy, building vast structures around the black hole to extract power. They might use the black hole's gravity for propulsion, slingshotting spacecraft to relativistic speeds. They might even use black holes for information storage, encoding data in the quantum state of infalling matter, though retrieval would be impossible. But for you, personally, falling into a black hole offers no benefits. It's not an adventure, it's not exploration, it's annihilation. The physics is clear, the outcome is certain. There's no loophole, no trick, no miraculous escape. Once you cross that horizon, you're gone. Final reflections on the abyss. We've explored this question from every angle. The physics, the mathematics, the thermodynamics, the alternatives, the paradoxes. We've considered different types of black holes, different ways of falling in, different theoretical frameworks. The answer is always the same. You die. The details vary. The timeline changes. The specific mechanism of destruction shifts. But the outcome is inevitable. Black holes are one-way passages to destruction. They're the universe's most efficient killing machines, using nothing but geometry to guarantee your annihilation. Yet there's something profound in this finality. Black holes teach us about limits. They show us that there are boundaries in the universe that cannot be crossed in reverse, places where the normal rules cease to apply, regions where reality itself reaches its end. They remind us that we're small, fragile, temporary, that the universe contains forces far beyond our control, that there are questions we can ask but never answer through direct experience, that some doors, once opened, cannot be closed. They also teach us about the unity of physics. Black holes sit at the intersection of gravity, quantum mechanics, thermodynamics, and information theory. Understanding them requires understanding how all these fields connect. They're not separate subjects. They're different aspects of the same underlying reality. Black holes force us to see the connections, to build bridges between disciplines, to seek a unified description of nature. In this sense, they're not just destroyers, they're teachers. If you fell into a black hole, you'd be participating in one of the universe's most extreme phenomena. Your destruction would be thorough, but it would also be meaningful. You'd be testing the laws of physics in their most extreme regime. You'd be experiencing what no human has ever experienced. You'd be crossing a boundary that separates the knowable from the unknowable. And though you couldn't return to tell the tale, your fall would leave its mark. The black hole would grow slightly, the event horizon would expand, the entropy of the universe would increase. And billions of years later, when the black hole finally evaporated, the information about your quantum state would emerge in the Hawking radiation, scattered and scrambled but preserved. This is cold comfort. It doesn't make your death less final or less terrifying, but it means that even in the most extreme destruction, the universe doesn't truly lose anything. Information is conserved. The laws of physics remain consistent. Reality continues. The black hole digests what falls in, transforms it, and eventually releases it back out in a different form. You're not preserved as a person, but you're not erased from existence either. You're transformed into something else, something that will eventually rejoin the cosmos. What if you fell into a black hole? You'd die, but you'd die in a way that teaches us about the deepest nature of reality. You'd cross the ultimate boundary and see, even briefly, what lies beyond. You'd experience the most extreme physics the universe allows. And you'd become part of the black hole, merged into its structure, contributing to its mass and entropy, until trillions of years from now it returns you to the universe as radiation. This is what happens at the edge of reality. This is what awaits in the darkness. This is what physics tells us about the most extreme objects in existence. The journey would be brief, strange, and final. The experience would be unlike anything else in the universe, and the ending would be absolute. There's no coming back. There's no escape hatch. There's only the fall, the disintegration, and eventually, the slow return as scrambled information in particles of light spreading through empty space billions of years in the future. This is the fate of everything that falls into a black hole. This is the answer to the question. And this is why, despite our curiosity, despite our desire to explore, despite our drive to understand everything, we stay away from black holes. Because to approach too closely is to accept your destruction. And unlike almost every other danger in the universe, this one offers no hope of rescue, no possibility of escape, no chance of survival. Just the cold, mathematical certainty of annihilation, followed by an incomprehensibly distant transformation back into the universe that once contained you.